Chapter 9, Mathematical Induction. So prove with mathematical induction that the following equation is true. So what we have is this left-hand side, also this right-hand side, and what we're doing is proving true using mathematical induction. So there are two steps with a mathematical induction. Let's write those down. So for mathematical induction, so we have the first step, step one. What we're going to do in step one is verify the very first example. So verify that the result is true for n equals 1. Verify the result is true for n equal to 1. And step two, which is actually the toughest step, we're going to assume the result is true for n equals k. So assume the result is true for n equal to k, and prove the result is true for n equal to k plus 1. So the theory here is if we could prove the first part is true, then we have like very early steps in this equation to be true. And now proving for n equaling k, what we're doing is assuming that it's going to be true for here and proving that it's true for here. So we could take this on to infinity and assume this is true for every single value in existence. So if we prove that in this case, k is equal to 1,000, we're able to prove it for n equaling 1,001. If we were here and letting k in this case be 1,000,000, we're proving it true for 1,000,001. So we could continuously push it further and further right, proving this entire thing to be true using mathematical induction. So let's give this a try. So starting off with step one, we're saying that the result is true for, or verifying that the result is true for n equal to 1. So what we're going to do is prove that this left side is equal to this right side. So we could start with just this value right here. So proving it true for the first one. So step one, verify that that's true. So for step one, we're verifying that the first term is true. So what we're saying is 3n plus 2 is equal to n times 3n plus 7 over 2. So we're proving those two true. So plugging 1 in for n. So 3 times 1 plus 2 should be equal to 1 times 3 times 1 plus 7 over 2. So left side, 3 plus 2. Right side, we have 1 times anything, it's going to be itself. 3 times 1 plus 7. That's going to be 10, and we're dividing that by 2. So we have 5 on the left side, 5 on the right side. So we just figured this part out. This entire thing is true. So step one is complete because step one asked us to verify that the result was true for the very first term. So for n equal to 1. Step one, done. Step two is just a bit crazier. So let's give ourselves a little bit more space. So step two, we're assuming that this is true up to n equal to k. So we're assuming that everything is true up until we get to the part where n is equal to k. So let's prove, or let's state what our true statement is. So 5 plus 8 plus 11 plus 14 plus ... plus 3n plus 2. But here we're saying that the kth term is going to be true. We're assuming up to the kth value that this is true. And we're going to do the same thing over here. So here, instead of n, we're proving that the kth term is true. 3 times k plus 7 over 2. So we're assuming this is true. And now we're proving that the following term is going to be true as well. So we're proving not only up to k, but we're proving up to k plus 1. So what we're going to do is rewrite this whole thing and then adding the next value. What we're going to do here, though, because we're not adding additional values, instead of writing k, we're going to write k plus 1. So let's rewrite this left-hand side. Plus 11 plus 14 plus ... The kth term, this right here is the kth term. And now we're getting the following one. So what's 1 more than k? It's going to be k plus 1. So we're adding 3 times k plus 1. And that's what we have there. Over on the right side, this should all be true for up to k plus 1. So k plus 1 instead of k times 3 times k plus 1 plus 7 over 2. And there we go. So we're trying to prove this to be true. But now what I want to show you is that this here is true. So we're saying that this here is equal to this value right here. We've already accepted this to be true. So we're going to accept this to be true down here. So we know that those 3 highlighted parts are all equal to this right here. So this highlighted part, which is exactly as this highlighted part, which is, we're taking this to be true. What I want to do is, instead of writing this here, I'm going to write this because it's a lot easier to work with. We already have this equivalence. We've already established that those two are true, or those two are equivalent to each other. So we're going to replace all of that with that one. So instead of writing this right here, we're going to write this as k times 3k plus 7 over 2. We still have this part on the left-hand side of our equal sign, so we're going to add that as well. So plus 3 times k plus 1 plus 2. And we're keeping the other right-hand side. So that part is what we're trying to prove. We're trying to make the left-hand side look just like the right-hand side. So this, because we have a fraction on the left side, I'm going to put this over 1. Let's rationalize this so that way we have fractions that we could add together. So far we have k times 3k plus 7 plus, we'll do 3 times 2, that's going to be 6. So 6k plus 1 plus 2 times 2 is 4. And all of this is going to be over 2. We're trying to get this to look like k plus 1 times 3 times k plus 1 plus 7 over 2. So let's try expanding out the numerator. So distributing k here, distributing 6 here, and see what we end up with. So 3k squared plus 7k plus 6k plus 6 and plus 4. We're dividing all of that by 2. We're trying to get that to look like this left-hand side. 3 times k plus 1 plus 7 over 2. Let's still combine these. So that would be 3k squared plus 13k plus 10 over 2. And this should be equal to k plus 1, 3k plus 1 plus 7 over 2. Let's factor this inside part. So 3 and 10, so factoring that to two numbers that multiply to 30 but add to 13. Looks like it's going to be 10 and 3. So factoring by grouping. So 10k plus 3k plus 10 over 2. Let's group the first two terms together, grouping the second two terms together, making sure that there's a plus in the middle. Looks like we could factor out a k. 3k plus 10. Can't factor much more out. So we have 3k plus 10. And it looks like when this factors, we have a k plus 1 times 3k plus 10 over 2. And with one more step, let's get that k times, or 3 times k plus 1 there. 3 times k plus 1. So it looks like we took 3k out of here. So instead of 10, we could have made this like 3 plus 7 and factored from there. So it looks like we have a 7 left over in there. Oh, which is exactly what we needed. K plus 1 times 3 times k plus 1 plus 7 all over 2. So those two are exactly the same. So we're taking that as true, which is proving that last step in mathematical induction. So step 2 was that we assumed that it was going to be true for the kth term, and we were to prove true for the following term. So for the k plus 1th term. And after a bunch of math here, a bunch of simplifying and trying to get these to look exactly like each other, we ended up doing it. So if you need another example or have any questions whatsoever, please feel free to let me know. Please contact me. But this is the last video of the semester. I hope you all had a ton of fun, just like I did. And if you guys ever need anything from me, please feel free to ask. Do not hesitate whatsoever. But I wish all of you the best of luck. And I hope to see you guys again soon, or at least meet you guys in person, because this has been a terrible online class, if you ask me. But let me know, guys. Bye.